Now let's get more into these volcanic hazards, right? The funnest bit of this. So one volcanic hazard is just the eruption column, the huge amount of debris that goes into the atmosphere. And when that debris goes into the atmosphere, it can cause a lot of damage, including to air traffic. Okay, so you can imagine if a plane flew through one of these ash clouds, these eruption columns, that ash could get into the engines, clog the engines. It could cover the windows and make it impossible for the pilots to see. So this is a picture of a plane that actually flew through an ash cloud, which is very dangerous. And it's estimated that about 6 eruptions per year are explosive enough that they rise up into the stratosphere and endanger air traffic. And then in the last 30 years, about 80 modern jets were damaged by volcanic ash. 10 airplanes experienced temporary in-flight loss of engine power, losing height very rapidly. So if you're ever in a plane and the captain comes on the intercom and is like, hey, by the way, there's an eruption ahead. We're going to turn back, or, we're canceling this trip, right? Don't be upset about it because that's very important. It's very dangerous to fly through these volcanic columns, eruption columns. The most recent one I remember that was just totally disruptive to world traffic flow, air traffic flow, was back in 2010. There was a volcanic eruption in Iceland. I'm not even going to try to pronounce that name, but you can see it there. And in this image, it's showing just how far the ash and the debris spread out in the atmosphere. It went all the way over to North America, all the way over to Russia, basically covered Europe. And during this time, all air traffic around this area was totally shut down. Right? It was the largest air traffic shutdown since World War II. That was a huge deal. Continuing to think about extrusive igneous bodies, now we're going to talk about the types of volcanoes. First, we're going to talk about composite volcanoes. Composite volcanoes, these are the triangular shaped ones that are formed from this andesitic and rhyolitic magma that has a high viscosity resistance to flow. And when the volcanoes form this triangular shape, we call them composite volcanoes or stratovolcanoes. Both words mean the same thing. And from these composite volcanoes, we can get these huge eruption columns that contain ash, but they also have what we call a pyroclastic flow. A pyroclastic flow is basically that ash that is so dense, rather than rising up into the atmosphere, it just basically races along the surface of the earth, kind of like a landslide, but rather than being made of land and earth, it's just made of ash and volcanic debris. And both of these, the ash cloud and the pyroclastic flow, after they settle back to Earth's surface, it creates what we call a pyroclastic deposit. You actually can see a layer of ash and other debris preserved in the sediment record. And so here's a picture of that. You can see this man walking along this outcrop, and there's many different sedimentary layers, and you can see those really dark layers that he's looking at, right? That's volcanic eruptions. And if you know the exact date of a volcanic eruption that created that layer, you can use that layer to date the different layers in stratigraphy. We call this tephra chronology. This actually happened to me. I was out on a ship in the Pacific Ocean off the coast of Oregon, and we were collecting sediment cores, looking at the mud there, and we just kept finding this like weird sticky gray layer that we weren't expecting to find beneath the mud. And after a while, my colleague was like, hey, we're off the coast of Oregon. We're really close to Mount St. Helens. She's like, I bet this is the eruption from Mount St. Helens. And I think it was, which means that we could identify the exact date of that layer. That was 1980. That was the Mount St. Helens eruption, which was super cool. All right, getting back to pyroclastic flows. Again, pyroclastic flows, it's that part of the debris that's so large, so dense that it doesn't go up into the atmosphere, instead it just runs along Earth's surface. And these can be terrifying. Think of an avalanche that's on fire, basically. It's an avalanche of hot ash, gas, debris from these silica-rich volcanoes. They can travel at 300 kilometers per hour. That's almost 200 miles per hour. Their temperatures can be up to 1,000 degrees Celsius. They are immediately deadly. Like there's no way you can survive one of these things. If you get it when it's still hot and fresh, right? I have heard tale of people surviving if they experience just the tail end of a pyroclastic flow, but it is very rare even to survive those. Next, we're going to talk about a lahar. Think of a pyroclastic flow and add some water until it turns into a slurry and you get a lahar. So it's basically a mud flow that's on fire. Lahars, again, they can flow incredibly quickly. And again, there's basically no way to survive them if you're in the path. When I used to live in Seattle, Washington, we lived next to Mount Rainier, and I remember thinking, if Mount Rainier explodes, we're probably far enough away that we're not going to be buried in ash, we're not going to be covered in lava, but we might have been close enough for that lahar, right? That huge mud flow that would come down the volcano. Right. So although volcanoes can be active over very long periods of time, and they can go through dormancy and then come back to life, they do eventually go extinct, right? No volcano is active forever. And during the life of many composite volcanoes, the lavas tend to become more and more silica rich. So more and more felsic, more and more closer to rhyolitic. And some volcanoes can actually start as basaltic shield volcanoes, and then over time, as they age, develop into rhyolitic composite volcanoes. So why do you think this is the case? How is this possible? What would cause it to gain a higher silica content, basically? Right, well, thinking back to last week's topic, how we talked about magma differentiation, mineral differentiation, crystal differentiation, right? The increase in silica content with age comes from the differentiation of magma chambers at depth, right? Most cases, this results in the increasing degree of assimilation of crustal rocks, right? So as that magma chamber ages with time, remember the mafic minerals will solidify and crystal out and sink to the bottom, so the magma itself becomes more and more felsic. And then also over time, with that, that heat transfer, the basalt or the granitic rocks of the continental crust around that magma chamber are also being assimilated into the magma. So those two reasons cause the magma to get more and more and more felsic over time. So as a volcano ages, it also gets more explosive and more dangerous.